New phone stand, which means like a proper phone stand, because I used to have a pile of books on my bed and in my laptop sitting on that recording. But I'm actually using my phone because I cleared out my storage and I have a cool phone stand. So I should be able to record videos with maybe better quality because I think my phone has better quality. And at least I know where I'm looking when I have to look at the camera. Hello world! Spoilers for a different video. For the sake of avoiding the possibility that the camera doesn't catch the lighter colors like the green one, I'm going to try not to use it, but I am going to use it at some points which might not be too important to see. I just knocked the phone stand over like a doofus. I hope it's in the right position, guys. Proof by induction is a very niche kind of proof that works in certain scenarios, but it's still chef's kiss. It's so much fun to do, and once you get the hang of it, it's just kind of satisfying, the idea that it always works. But basically, it's often used as an analogy with dominoes, which is kind of a good way to describe it, where if you knock over the first domino in a row, it'll knock over the next one, and the next one, and the next one. So you barely had to do anything, you just had to knock over and nudge the first few, and then the rest of them fell down because of it. So it's the same with proof. Like I mentioned before, this is a pretty niche form of proof, and in Further Pure 1, they basically show 4 main ways that you can use it, very related to the topics that you covered Further Pure 1. Let's go through one of them as an example. In FP1, there are 4 main different ways that we can use proof by induction to prove these 4 different concepts. There might be some sort of sum you can prove, some sort of rule that something divides something else. You can prove that a sequence can be written in this form instead of another, or you can prove some sort of theory about matrix multiplication. In order to explain the concept of proof by induction, I'm going to be explaining it through matrices, because I think matrices are quite a cool one to use, and it's also quite simple when it comes to the actual calculations. So we can focus more on the method than having to figure out the algebra. Here we have a very common question. Prove that 5 minus 8, 2 minus 3 to the power of n is equal to 4n plus 1 minus 8n, 2n, 1 minus 4n. For any natural number n, so any positive integer value of n, 1, 2, 3, and so on and so forth. How could we prove this? Well, it's very common to first try and prove it for n equals 1, so this is kind of like a base case, which basically means, okay, let's just make sure this is true, at least for the first value, because if it's not, why even bother? And it also just helps to set up the mindset, okay, this could be possible. It helps convince you a bit already. So to prove that it's true for the base case, then we check, is it true for when n equals 1? Well, any matrix to the power of 1 is just that matrix. And then on the right-hand side, we just have to plug in the values for 1. And if you do the arithmetic and find and simplify the whole right-hand side, you'll end up with 5 minus 8, 2 minus 3, which is the same as what we have on the left-hand side. So it is true for our base case. Okay, I feel a little bit more convinced, but now shall we try and prove it for when n equals 2, and when n equals 3, and when n equals 4, and when n equals 5, and all the way up until infinity? Well, no. Do you have all the time in the universe? I didn't think so. Sorry, you're mortal, not a cool god. So instead, what we're going to do is we're going to be smarter than any cool god, and we're not going to sit here forever and instead say, okay, but what if it were true? And this moves us on to our second step, the assumption. The second step is that we're going to assume that n equals k, which is also some natural number. And we're going to assume that it is true for whichever natural number k is. That's basically your whole assumption step. You basically just tell them, hold on, hear me out. What if n equals k? And you're done. This is the easiest. You basically just replace n with k and you're done with this step. And now we come to the heart and soul of proof by induction. We're now at the induction step, which is where we're going to say, what if this time n was k plus 1? Let's do it, and then I'll explain why we did it. Well, we know that if we have to replace n with k plus 1 this time, we just replace wherever n is with k plus 1. But we also know that if we have a matrix to the power of k plus 1, that's the same as that matrix to the power of k multiplied by itself ones. So here I have two matrices, one which is the matrix 5 minus 8, 2 minus 3 to the power of k multiplied by its original self. And we've already assumed that if it is written to the power of k, then we can write it in this form that we have in the question. So because we assumed it was true for n equals k, we can replace this power of k with the thing that we've assumed for. If we have n equals k and we're adding one more of the matrix to it, it should give us this same result. And if it does, then that means that we've done everything correct. So now let's try to do a little bit of matrix multiplication and simplifying to try to rewrite this into this exact same form. So after a little bit of matrix multiplication and simplifying everything and then factoring out k plus 1, we can see the forms that we wanted is the same as what we were expecting by using our assumption. What does that mean? Well, since we assumed that it is true for n equals k, what we've just shown is that it has to be true for n equals k plus 1. So if we said k is equal to 1, which we've already proved is true, then that must mean that it's true for k plus 1. So 1 plus 1 would be 2, so it's true for when n equals 2. And then by the same logic, since we know now it's true for n equals 2, it has to be true for n equals 3. It's true for n equals 3, it has to be true for n equals 4, and so on and so forth. And that's why it falls almost like dominoes. So thanks to this method, we're able to prove an infinite number of possibilities just in 3 simple steps. And then we've basically finished the proof. All we have to do now is write a little conclusion to summarize everything that I just said. This is quite rare because usually maths is just equations and solving, but in this case we just have to show everyone and write a little conclusion to show, congrats, we did it, yay! So what we have done in summary can be written into 4 simple sentences. We have shown that it is true for n equals 1, we assume that it is true for n equals k, and therefore shown that it is true for n equals k plus 1, and therefore because of that we know it must be true for all n which are natural numbers. If anyone doesn't know, these 3 little dots are just a little shorthand way of writing therefore. Mathematicians are really lazy, and if you want, in your answer you can use these 3 little dots to really quickly write therefore instead of having to write the full thing. Because who even wants to write in math? And that is the entire concept of proof by induction. We can also use this to prove different summations by looking, is it true for n equals k, and then showing that it's true for the next term by adding on the next term of the sum. We can show that it's true for a sequence where we look at a certain term in the sequence, the kth term, and then we can prove that it's true for the k plus 1th term. And we can also prove that it is true for divisibility rules, which is where if we have some combinations of n's, we say that n equals k, then it must be true for when we replace it with k plus 1. I don't have time to go through the other 3 methods, but it's the exact same style where you follow these 4 steps. If you guys would like to see me go through them, feel free to comment and I might make a video about that too. Thank you very much for watching. I hope you enjoyed this video and I hope that the camera is good. Please tell me if the quality is better. I really like the stand that I got. I think it's pretty fire. It makes me very happy to be recording with such a good quality, so hopefully all the text is readable. Hopefully the green pen is also readable. I'll be checking that out when I'm editing. Goodbye, S-Bears.